I still remember on my first day at Caltech, so I met Lina. And so it's been a while. And during the process, we coupled together to North California. And I also remember when I was writing my career proposal, and Lina gave me a lot of help and suggestions. And so, yeah, without further delay, yeah.
Thank you everyone for coming to the workshop. As organizer, Li Jun and I were planning to be relaxed, don't do the presentation, but we got some last minute cancels and I'm filling up. I think we got probably 2 cancellations. I forgot which one I'm actually replacing. Yeah, so. It's a great honor, actually also speaking after my own student, Guannan, and I can continue the story, why Guannan didn't come here, but come to my group, and actually thank you, Steven.
So this is the proof why Lina is much smarter than I am.
So I will start the presentation using my old slides back in 2013, before I graduated. And for the slides, so I was on job market. This is actually the slide using in Cornell Chalk Talk. The Cornell forced me to do the Chalk Talk, which I have no idea what my vision is. And so it's borrowed or stealed from Steven's slides. I don't know whether Steven remember the blog I used. When we started, I think when Steven started, say the group that's working on power system, we try to figure out, every year, we'll try to revisit what the remaining issue, what the problem issue they're working on. And the slide of Steven's slide has more details. Theory will have details. What kind of theory have been developed? What theory we want to have? Lin Wenko should remember, right? You also forgot this kind of slides. And algorithm and application. So I use the slides. I have been using the slides since 2013, even still now. This kind of shaped my research vision deeply, how to making the theory, algorithm, application really coming together. So when we do the Chalk Talk, I was worried about the people who really know power system claim, Lina, you haven't done any application, so that's why for my application part, I just say to start. We haven't really done any real application, as I was doing the Chalk Talk. So one big thing I think I learned from Steven is kind of try to build a theorem working for application, don't sacrifice anything. It's still very, very hard. And I think right now I'm kind of telling my student, you probably, if you do theory, you can sacrifice application a little bit. If you do application, first forget the theory, to see what much you can do, because otherwise probably the student will stop, Lina cannot do it. But still, this is eventually we're trying to close the loop. Another thing I really learned a lot is how to really working on a new field. So I was lucky, I think Steven just coming, when I was at Caltech, Steven just coming back from a startup looking for a new field. And I remember, so I didn't know power system. I have no idea work on power system. My advisor, John Doyle, I want to do biology with John. So I still work on biology with John. And there's a reading group going on. I see there's a lot of people, students. What's going on? Why every day at certain times, a few people sitting there together, what are they doing? And then Li Jun told me, Lina, they are doing some new things like power system. You can't just sit in. Ask Steven, can I just join? Steven is very open-minded. Okay, yeah, sure, Lina can come. So I kind of come and go because I still have a project with John. We were working on a very exciting thing on the heart rate variability, but it's also very, very challenging. So a certain time I was discussing with Steven, probably I still want to spend 1 year, not worry about power system, just for the heart rate variability. And Steven was so kind. That's my last point, is unconditional support to students. Steven told that to me, Lina, go ahead to focus on the thing you want to work on. If you want to work on power system later, you are always welcome to come back. With that assurance, just spending 1 year, we closed the project. We didn't publish the paper, but I think that's the year I made the most progress with John, doing all the experiments, putting all this data, try to tell people, the physiologists, what's the story we want to have. And once I conditional support, it's not just when I was a student, so that's back to the Guannan story. When I started my job, one big worry is how I'm able to compare with John, with Adam, or with Steven, right? The student, they want to go to work with them, not working with me. Especially, I was planning still working on power system, and Steven is so well known. I remember during the first couple of years, when I was looking at all the student application, I will also email Steven. Who are you planning to admit? Steven actually will reply to me. Steven will ask me, Lina, what's your preference? So kind of like, okay, for Guanlan story different. I think Guanlan was very honest. Guanlan during the interview, I was asking Guanlan, like, if you got offers, how are you going to decide? He always told me, if Steven give me the offer, I might go to Caltech. And then I asked Steven, and Steven told me, oh no, Guanlan is not on my list. I'm like, glad. And since 这个也是 for 风雨, like other students similarly, I asked Steven. So it was great. I think that during the first couple of years, other people asked me, my colleague, junior colleague, Lina, how do you recruit students? They know how amazing Guanlan is. I told them, for me, I'm kind of easy job. I can talk to my advisor, what they go to admit. Sometimes they'll just say, Lina, you go ahead admit first, and then I will figure out what I'm going to admit. So thank you so much, Steven. Regarding the research funding, similarly, I think the first couple of years, I was unlucky to get funding. And as I was trying to put in a team, I asked Steven to join the team. Steven said, Lina, this is very time-consuming. How about you join my team? And then about the budget, Steven told me, Lina, how much you need? Just go ahead to think about how much you need. Then we're working on the rest. So that's actually, I think, my top 2 grant during my first 2 years, and helped me to get started. Thank you so much. I'm trying to be that kind of advisor to my own student. Hopefully, like, it's still far away, like it's the bar too high, so hard to achieve, but I'm trying it. So today, like, I think not much time. So I will just kind of give you some quick update of some application, not the theory. The one thing I really want to do is closing the loop between the theory and application. It's still a challenge. I'm not going to talk about power system. One advantage being staying in Harvard is I was the only control person there. People throw different application to me because they have questions and they don't know how to do it. And the one motivation why I was doing learning is not because learning RL is popular topic. It's because the problem my colleagues throw to me, I don't have any solution. Like this is some examples I've been working this since Guanlan. After Guanlan left, like we actually eventually making some progress. So this is the House Zero project. We spent since the first day I joined Harvard. I know the director, so it's a real house, but welcome to visit. It has all those IoT sensors, including everything. And we're not trying to just say the power efficiency. The architecture designer want to put in another, like, let's just totally remove those mechanical active components, like to see how passive we can do. When we say passive, it's not like the HVAC system. You're actually using the geothermal. And also for the ventilation, close, open the window. Like go back to the old days and to see how much the passive control can really do. So this is the project we started, and it's been 10 years. So the Power Grid, we have been still collaborating. I'm not going to talk about Power Grid. Like Steven did a much better job. And this is from the MGH, the hospital. I will talk about a little bit things, like what's going on with that one. And this is a very exciting thing, like putting a lot of time on this project, is had bioengineer, had a very fancy nano flexible device. So they can look at that. This is a cardiac organoid tissue, the real bio tissue. So the device they have, they can implant the device on those soft bio tissues, target the individual cell, can do the monitoring, can do the simulation. So now the question, how are you going to really control it to help in the biosystem to grow, to function? Like there's no model. So you look at all those, like the common things is the power system has some model, everything else, there's no model. This one was that we're not really doing the HVAC. We were really like targeting the natural ventilation. Like if you're doing the model, it's going to be PDE model. Like I don't know what really the PDE control can do. That's going to force me to, okay, let me really think about how can I use in the data. Show you some result, like I will put in how much time do I can try to 5 minutes or?
Yeah, at least 5 minutes.
Okay, thank you. So that's putting that is like the challenges, right? So I've been looking into what's really the main knowledge, the system structure, the representation. So I was still talking about little bit theorem, but the theorem like probably will take 1 hour. So I only have 1 slide to start with the theorem I'm talking about. This is a control, like almost everyone in this audience know this kind of problem, right? We're going to have, what didn't work? So a technical issue was.
Always just do the unplug. It's the computer.
I think it's not, that's my computer freeze.
Oh, nice.
Okay, good. Not sure what the projector on my computer. 1, 2, 3. So like we put in a general formulation. I was also heading to doing the non-linear stochastic thing, like just complex, just non-linear, like what we are able to do. So we have the state transition, action, reward, discounting, feedback policy, and lots of IO people using unit pendulum to show the case. So I think when I studied IO, like during the last 2 years at the time, my own group, so kind of follow studying the new field. So we're studying a new field. Let's just go ahead to learn what is the learning approach we have. So we started doing the learning. And when Guanan was here, I didn't ask Guanan to try those deep learning neural networks thing to do it. After Guanan left, we actually go ahead to let's test those kind of open GitHub toolbox we have been built to see how it's functioning. Unfortunately, like I also tried by myself, I was not unlucky, right? If you give me a system, I tune the parameter, my code is not going to work. And my student, like now I have one student who is really able to tune things well, but it's very time consuming. You don't know what's going to work or not. Like typically the IO algorithm has actor, critic. You're going to parameterize the policy by the neural net. You're going to parameterize the Q function by the neural net. So yesterday, Srikant gave a very good introduction of those. But that's a frustration. So if I really want to use the system to the real physical system, and it's really like the system is a real one, I don't have a simulator, I don't want to just kind of, I have no idea how to really tune it. When I was saying the small network is still big. For each layer, you got probably 256 neuron, and you have 3 layers. That's to the power of 3. So it's actually like not that small if I'm thinking about I want the flexibility of the control policy. So that's for us, we're trying to think about what's really the good representation. Once the representation is what kind of neural net I can really use, which will, like we know transformer is good for large language model. But for dynamical system, do we have something natural from the system? As I don't have time to, this is going to be 1 hour talk. Hopefully one day we'll come back to the Caltech to talk about the theoretical work for this part. So we first try to look at the Q function, the representation for the Q. That's why I was asking in 3 kinds of questions about the Q assumption. Theoretical work, people are just going to make assumption. The Q function approximated by a neural net with certain accuracy. But where does that come from? So we dive into that. We had we call it state transition. So we figure out one representation, which is actually a very general representation. We first figure into the specific, like the example I'm familiar with, even the pendulum, the controller, and then also using the OpenAI to see what is really like work in the OpenAI gyms. This is for the critic. And we also, like I reached out by the PDE, partial derivative equation control people. They also asked me, Lina, like, how am I going to really design the PDE control with 3 dimension, even higher dimension? So I said I don't have a detail to talk about. So we also further to figure out what's really the feedback control policy that I can use for those kind of system. And the way we've been kind of using is some combination with some comparison same thing. But we also design algorithm to automatically tuning those icon points. So it's kind of can think about that clustering, but the cluster is not being fixed. So you need to learn dynamically figure out how the cluster is going to do. For each part, there's still some function you actually can impose, put in the neural net as representation, but each component has a meaning. So as I don't have time to dive into details. So this is the sum. Let me see. At least so far, we tried the inverted pendulum, and this is outcome control policy. You can actually see very nice symmetric from the learning, which makes sense. For the inverted pendulum, for the 2 direction, it has a symmetric. So further, what you can use in like the advantage for the representation is give me a systematical way to figure out what's really the neural net, the new things I need to add. If I start with a small neural net, that doesn't work, I go bigger. But how bigger, what systematic way to add, I'm not going to waste the learning things that I did before. So that's why it's connected with the sim to real. For the sim to real, like simulation, we always see cool videos. And reality, you can always find in those unfortunate videos going to happen. And this one was actually from my own lab. So I started building my own robotics lab in the past few years. But let's see, look at with the representation. So this is just if I train RL on the simulator, then what's going to happen? So we did one benchmark. I using some representation I learned, but not really like rechange my representation, doing the RL again doing better. It's kind of skill transfer policy, not going to work. The test is actually pretty simple, just like go ahead and then stabilizing, then coming back. But then once we add our representation to multiple rounds, it's actually 10 rounds. The student was very impressive. So he did all those demo things within a week. And that's also demonstrated that once you really have a systematic way to do it, you know how to really make it work, and it's working like a magic. So we are still continuing on this topic, like now it's a single agent, how we're going to do the multi-agent, if you're doing the multi-agent, the coordination, and ultimately, hopefully one day, I can really put in a group of drones flying outside. Right, let's just go ahead to adapt. So now I'm going to quickly to show you some simulations. As I said, this is a real building, real house. So people actually study inside. This is our real office building. So you look at the device, it's different from the HVAC system. I'm not going to dive into details. So the one biggest difficulty is the natural ventilation model. So that's why we actually did a model-based method for this one. We have a lot of experience trying both model-based and model-free. Eventually, it's a combination of both model-based and model-free. So we did a model-based for the offline training. Eventually, the model actually worked for this system. It's doing the STM. And the long-term prediction is because of weather. It's actually you're going to predict like 12 hours ahead. We also have the short-term prediction because for the window opening. So we need to estimate the ventilation quickly. So eventually, this model becoming the best. We simulated and implemented on the real house. I'm putting also comparison. One conclusion is this. So we actually can have greatly improved, especially for the air quality. And for the temperature constraint, it's also much better improvement of it. So there's a lot of, right now we're trying to scale this house zero control to the larger system connected with the grid. So we're actually writing a big cluster proposal recently with a building designer and all the people together, and also the PDE people trying to build a model. And this is a different one. So this is I rejected the collaboration early on. See, it's a radiologist come to talk to me, Nina, can we build an autonomic ultrasound? So for me, this should be a simple one. Why I need to build an autonomic ultrasound? So this application model is typically for the patient. Once you finding some illness, you will go there, do a very thorough check. You will have your CT image, which is a 3-dimension. And then you have a follow-up. So if we don't have those things, for me, I had experience. I scheduled the ultrasound, wait for 2 months just for ultrasound. And I didn't drink enough water. They asked me to come back again in 1 month. That's 3 months. After that, I then reached out to him again. OK, let's collaborate. Now I know why you're saying that. So for the CT scan, if they're for the cancer patient, not going to have so my dear friend who has cancer is every year, she probably go back to visit. So you can imagine for different type of cancer, 1 year is really too long. So the ultrasound, and the reason the CD has the radio, those kind of X-ray things, so that's why you also want to minimize the time you're doing the CT image. So this is for the local, the ultrasound is just 2D image is non-invasive, so actually can do it more often if technician is available. So it's kind of the one, you can go to the local clinics, you just take in the images, and then probably the image can send it back to the hospital and then to do it. So for me, I think this problem, this should be simple. This is a manipulator, and this manipulator is very easy to control, and I don't need to grab anything, right? The prop is already there. But the challenge is this, once I really started thinking myself as a robot doing it. So I don't know how to really understand the image. I need to do the real-time image processing. It's not offline. There's a lot of offline image processing algorithm can do very nice. But this one, we need to do the real-time image processing. And there's no map. If you look at the ultrasound, you will see the ultrasound image later. You don't know what's really going on. You don't know where you are. The technician, that's why technician has a multiple years training. And so safety. Another thing I think as a patient, always worry about me, seriously, this is a robot going to touch my belly? No. So all those constraints, and we try to figure out what solution we're going to do. I will just have one slide to show you eventually. It took us we started in 2020, so 4 years, to eventually have one demo. So the difficulty, even including to hack the ultrasound machine, because no company give us direct access to the image at the real time. They give us the image after the entire process, but not real time. But we need the real time processing. Took us kind of 1 or 2 years to figure out the best way to hack the system. So first, this one actually not that difficult. You're just using the computer vision current methods. You can go ahead to find your initial contact. But not how to build a map. When we built the map, this is combination with a group of the radiologists. So we eventually decided to use this is the HV registration. So this is one of the major blood vessel in the belly. So it's because it has a very, you look at the features it has, so it's easy to build a deep learning model to do the image recognition. So we eventually picking that, first trying to find that landmark similar to the SLAM that people did in robotics. After that, then go ahead to taking more images to build a map. So that we call it 2D, 3D registration. With those, then later, since I had a CT image from the patient like last month, based on the image together, we go ahead to do this. This part is actually the RL algorithm. We did the local RL tuning to really find the target model. And you can look at here. So we had a, if you come to my lab, I will show you those demos. So you look at the ultrasound. Right? For me, I have no idea what I'm really looking at. So we trained the UMAP deep learning model for that part. Now going to take in more images to build a map. To construct. Once it's being done, we have the map. And then to go to the target localization using some local RL algorithms. Yeah. So I think like really closing, doing the real application, making sure everything is still eventually, even putting a demo, like I said, this one took us 4 years. During the middle of time, I want to give up, right? It's the student to graduate. And the student hasn't graduated. Now we actually just submitted the paper last week. And the PI, co-PI, let's submit to Nature. I think, let's don't do Nature, right? The student need to graduate. So if we change the paper now, like we don't know. So, but I'm very proud of the student. I got some like engineer kind of spirit student after Guangnan left, and they just, okay, let's make it work. So I'm not going to give it up. So I'm glad to have the student to support. And this is another crazy idea. We studied during the COVID, had no idea whether it's going to work or not going to work. As I mentioned, like, so he has a very fancy device. We started talking with each other. We meet every day during the COVID over Zoom to write a proposal. Funding agency, like without any preliminary data, they actually found us. Great. So we go ahead to start working on it. So the difficult, let me put it like the maturation. So why people believe is doable. Because from some like 2019, that's like 2020, we started working on together. People actually show if you can have the electronic stimulation, it can speed up the maturation process. So where does cell come from? Like from your skin cell, change back to the stem cell, you culture, then to the different organ you want to have. We pick the cardiac organ at the first stage because it's very homogeneous. So like so the brain is much more difficult because all the neurons are different. So this is the cardiac tissue. And the device he has can actually grow with the tissue. So the question is how to find the optimal stimulation policy. So this is actually standard feedback control question. You put in that, you have sensor, you have actuator, close the loop. And I was like, RL people claim this is definitely fit into the RL framework. But one biggest challenge, one experiment taking at least 60 days and expensive. And also one postdoc is full-time on that. So we don't like, no matter how efficient the sample complexity people claim on the RL method, it's definitely not that kind of. Like it's always going to be 10,000 if you look at all the simulation result. So this one, no, definitely not. So we spending a lot of time. Again, I think my student was very creative. For me, I kind of basically feel like I'm getting stuck, right? What does it mean? We don't have anything for those. Back to the RL, like what's the real observation I should have? What's the action? What's the reward? How to quantify it? Just like it's not fit. Even for those, I don't know. So again, that's back to the collaboration with the biologists. We're working together. We read the literature again. So first for the same reward, we change like whatever the signal is the electronic wave signal. We did a 2 years data analysis to map that with the still time. Still time is kind of the maturation status of the individual cell. And then we use that one. It's just like one measurement for individual cell to talk about how mature the one is. And it's kind of non-invasive, is that you don't need to kill the cell to know the maturation status. And the actuation so far is actually straightforward, just the electronic stimulation. And the algorithm, like not RL algorithm, we designed our own Bayesian optimization algorithm, which actually I can update every day. So when we started collaborating, really go ahead to try the algorithm. The postdoc and my student, they really meet every day to talk what the next day policy based on today's data. And so, like, probably I should, it's because we are applying pattern for this one. The CoPI is very sensitive about how public we can make in the result we have. But for this community, I'm going to show you some result. So this is our AI policy. And this means, like, this is still the time. Right, the higher means it's more mature. So from the figure, you can see with our AI policy, like this is day 40, almost all the cell, like is mature. And it also has, yesterday I showed more data to John, like John are lucky, like for some other side, I'm not going to show more. So basically like the AI policy after 4 years, we have a policy which can stimulate the biotissue. Kind of if you ask me, what exactly the physics I use, we definitely using a lot of domain knowledge. We also use the AI algorithm together. And the student was able even to write a pure theoretical Bayesian optimization paper, very big improvement performance. Now we are working on the Nature publication for this one. With that, I want to close my talk. Like coming back to this image, I think now I can say I did some application. And thank you so much, Steven. Happy birthday.
Any questions?
For all this, basically, traditionally you have a feedback loop, then you
Yes.
would have a nicely, you can actually find a function that actually have a nice structure, a nice property like convexity and things like that. But now all these applications, you don't have those,
They don't have those
functions.
structures.
So
No.
that you use neural network to actually do it. But what you lose is the mathematic property. Is that the way to think about it?
So, okay, two things. So like, first of all, I don't have time to talk about the theoretical work that we're talking about this one. So for this one, we actually had a theoretical guarantee about representation, how general it is. There's one part is, right now, if you look at all those theoretical RL paper, people have some assumptions. People will also assume there's some oracle. But oracle means is, like in the small steps, I probably still need to run some optimization. And that optimization, because it has a neural net, you cannot really claim you can really find the optimal solution, but the kind of typical people is a claim, right? You have Oracle to do it. And my criteria right now is at least you should, because there are also some algorithms, go to another stream, they put in a formulation. You even don't know whether there's any kind of thing to start with. They even know like genetic method to solve it. So now I think the one thing I'm okay with is right now is that you don't need to claim each step you're going to be exact. Because you put in neural net, you're not going to say that. But you have to making sure there's one method, at least SGD is able to implement it, and the computation complexity is managed. So that's kind of a story for this one. We have a theoretical guarantee. Like if you, for each small steps, you don't like say too much about the optimality. And overall, we can talk about the optimality of the control policies. We tested recently, so because we want to change this one to the large scale network system. So for that one, I need a benchmark. So those small systems have benchmark with the other people's approach. So we actually benchmark with the LQR. Because LQR, I know the linear controller, the optimal K. So we're actually using this method on the linear system. Even though it's kind of like overkill, why need using this method? But we're using this representation method, which has a neural net things. On the neural net, like the policy parameterization is a KX, but the Q is a deep learning. But the deep learning is from our representation. It's actually indeed recovers the optimal linear K.
I'm
Yes.
curious, like, without this mathematic property, like convexity, how do you know that the function as a controller would actually guarantee stability, for example?
That is a great question. So the typically is like, you see the reward function? Yeah. So typically it comes from like, if, typically that's all the problem for the RL. Like if you go, I put it as an infinite time horizon. So if you guarantee your cost is not going to be unbounded, then it definitely need to be stable for that one.
Oh, so stability
Yes.
becomes the optimization goal of the neural
Yeah, like
network.
it's because the cost will
And
capturing that.
interesting.
If your cost function include all the state deviation, yeah. So that's why I think for the linear system right now, I'm becoming more confident of the method because for the LQR, we actually really can recover the optimal K.
I see.
Yeah,
I think I answered too many questions, but this is super interesting. Thank you.
great.
Any other questions? Okay, no. Let's thank our speaker again.
Thank you.